So this is the kind of some of the mathematical background we're going to use throughout the course. In fact, not really, because some of it is the mathematical background. Some is a kind of a preview of some of the things we're going to introduce. And we could introduce a few more along the way when we need them. So that's kind of the whole list of things that I'm going to quickly show you. It's a bit of a challenging / risk to be extremely boring effort, because it's going to be a long list of definitions. Right? So the idea here is just to try to attach these definitions, some intuition of what they're for, and some pointers to what they are, so that you can go back and look at them. Essentially, we're going to do three things. The first is that we're going to try to remember what are vector spaces and abstract them a bit so that we can use them even when things are infinite dimensional. And basically, the notion of Hilbert space is just, for us, it's just going to be a vector space where things inside every element can be infinitely long. Okay, and we need to fix a few technical things in order to make sense of it. By no means we're going to do an in-depth introduction or technical introduction to this. We just give you pointers to what are the novelties with respect to the finite dimensional case. And then we move on from elements of the space to maps from the space into itself or into another similar space. So in the case of vector, these are the matrices. In the case of infinite dimensional elements, we call them operators rather than matrices. If you want, there are infinite matrices on both sides, potentially. And finally, we're going to just really give like a flash of 4 slides on some of the things we're going to use for probability theory. And it's really just a very short story. So let me just start by saying we like RD. Okay, that's what we like, and one of the reasons we like it is because we know how to do a bunch of things. So we think of the elements of RD as a list of numbers, and then once we have this list of numbers, we call them vectors, and we know how to sum 2 of these things. We know that if you multiply one of these things by a number, we still get one of those things. We know more. We know how to multiply 2 of these things. We call it a scalar product or an inner product, and now we don't get one of those things anymore. We just get a number. All right, and here I wrote on you see there are 2 notations. There is a symbol that describes how you compose any 2 elements, and then a specific definition of the actual operation you do when you have 2 lists of numbers. If you have 2 lists of numbers, you multiply each entry, and then you sum up. All right? And then given this, you actually can take norms. What are norms? It's basically the inner product of something to itself under square root. That's kind of the way we think about it. And here again, I give you the definition. And then we can take distances of any 2 things. And again, in the usual case, distances between 2 things are just the norm of the difference of the vectors. The difference of the vectors makes sense because, of course, you can sum, but also subtract things. Now we just to take the norm of the element, which is the difference of these 2 things. All right? Now, basically what we're going to do next is just we're going to take this and just appreciate the fact that what you write here makes sense even without everything you write on the right. Okay? So what do I mean? I can define an inner product, and it doesn't have to have this expression. I can just define abstractly what do I mean by an inner product, and gives whatever is a thing that is legally an inner product. Okay? So for example, if these were 2 functions, this wouldn't make sense, right? What are the Vj of a function? Yet I can define an inner product. Agree? And we keep on going with that. Okay? So to define an inner product, we don't have to have 2 lists of numbers. We just have to have any operation between 2 things that has a certain amount of properties. And you kind of already know this because you've seen product of functions before. And then we keep on going down, and the same story will hold for norms. And more than that, it turns out that a norm can be defined as something inner product itself square root. But in fact, doesn't have to be. There are legitimate norms that are not defined this way. If you just take the maximum of a continuous function, for example, is the prototype example of a norm that is not defined by any inner product. And again, you have to ask, okay, but then what is a norm? If this is not the definition of norm in general, then what is the definition of a norm? And you can keep on going. You go down and you say, oh, I have a metric. Or in this case, a metric is defined this way. But is this the definition? If you take 2 strings, okay, you don't really take the inner product of two strings. It's not the usual thing to do, and you don't really define a distance between two strings this way. Yet you can define something like the Hamming distance between two strings, and it turns out to be a legitimate way to measure distances. So it must be that there is a definition of this symbol, which is not given by the expression at the right. So this, everything which is not this symbol is an example, is not a definition. It's just one specific example. So we just have to go back because most of this stuff you've seen before, and we're just going to look at them and appreciate the fact that this symbol, and this symbol are a well-defined object that don't depend on each other. And it turns out that once we have an inner product, we are in the richest situation. We might have a norm, but not an inner product. We might actually have a metric, but not a norm or an inner product. So when you have an inner product, you're game. You have the maximum amount of stuff you can get, because then you can get norm. You can use these two lines to define norms and distances. Once you have a distance, in general, there is no way to go back. Same for norms. Okay? So this is the first game we're going to play. So RD is the prototype example of a vector space endowed with what we call the Euclidean structure. Okay? Euclidean structure refers to the fact that we have an inner product so that we can define everything else. What we want to do now is to just remember these properties and then abstract them further. Our goal in the end of the day is going to be to basically be able to do everything we said now when d is equal to infinity, or even more abstract situation. Why do we want to do that? Because we want to be able to deal with functions. And from a learning perspective, we want to deal with nonparametric models. So there is no precise definition of what we mean by parametric model or non-parametric model. There is always some kind of parametrization. But typically by a parametric model, we mean some model where we specify a priori a fixed finite number of parameters that we're going to use later on. Okay? By a non-parametric model, we mean a situation where in principle we actually allow the number of parameters to be infinite. And then we find a procedure that as soon as you seek data, automatically decide on a finite number of parameters to be used for that specific data set. There is a huge difference. In the first case, I chose the parameters number a priori. In the second case, the procedure that adaptively, based on the data, choose the number of parameters. The price I pay is that I have to be able to handle infinite dimensional objects to begin with. And that's the reason why we spend some time going into infinite dimensions. Okay? Again, stop me anytime. This is going to be not a super fun hour for you guys. So if you stop me along the way, there is a chance that at least some of you will stay away. All right, so what is a vector space? Again, if we take RD, we know what it is. Otherwise, the long story short is you basically axiomatize whatever you did before. Is a space. When we talk vector space or linear space, this is not a space that is made of list of numbers, objects on numbers, but just of objects, elements, with the property that you have two operations. One typically is indicated by the plus, and is the sum operation. It basically says if you sum two things, you obtain another object in the same space. And if you multiply by a number, this is typically indicated with a dot or nothing, in the same space. Okay? There's the closure axioms, and they're the main one, and there are a few others that you can derive from this. Okay? But it doesn't really matter. So whenever you hear me talking about vector or linear spaces, this is not RD. This is a set of elements for which I can perform these two operations. If you take elements, you can sum them up. Okay? If you take two strings, unclear. If you take two graphs, unclear. And that's exactly the distinction we made, yesterday. Okay, on things where you can do this operation or not. You can clearly imagine this is an interesting distinction because while we give it for granted and we really think RD, oftentimes you don't know RD stuff. And if you're doing RD, you can only start by taking the difference of two things. And that's a good start, for example, comparing things. But if you don't have the sum operation or the multiplication by number, it doesn't really make sense to take the sum of two things or the difference of two things. And you have to wonder a bit how you're going to handle the object in the space. Okay, so this is a very basic thing. Most of the time we're going to have it, but sometimes we won't. Okay, so we have to keep that in mind. So vector or linear spaces means this: a space where I know how to agglomerate two things or multiply by numbers. And you can be fancy here, but we're always going to consider real numbers where we use in this kind of operation. Okay? Complex numbers, even more general, but you don't care. These are real numbers. And again, Clearly, RD is a prototype example, okay? But take polynomials. If you take any two polynomials, you add them, and you can legitimately add them, and you get a polynomial. And if you get a polynomial, you multiply by a number, you get another polynomial. And any space of functions is the same. Take two continuous functions, you sum them up at every point, you get another function, okay? And that function is going to be continuous again. That's something you can check. And of course, if you take a continuous function multiplied by 5, you still get the continuous. Okay, and look, a function is not a list of numbers. Okay, so we already are familiar with this kind of notion in way more abstract things than RD. Now, an inner product. Okay, a word of warning about notations. There are basically two notations for inner product. One is the one that I had in the first slides, where you take a thing, you put something that looks like a T on top of it, and then you squeeze it to something else. That notation somewhat suggests that there is an order in the thing that you're doing, and it's typically used when you're dealing with finite dimensional stuff. Typically, when you deal with infinite dimensional stuff, you use this bracket notation, okay? It's basically angly parenthesis, and that's kind of a bit more democratic. The order doesn't really matter, and it means the same thing. We're gonna typically use this notation, okay? So whenever you see two brackets and a comma, this is just an inner product of two things, okay? So I'm not telling you any information about what it is. I'm just telling you the we're going to use for most of the course. What is an inner product, whichever notation you use? Well, it's something that takes two things and returns a number. Okay? We already knew that. But now we just to figure out what are the properties that make a function of two things that return a number something that we would call an inner product. Do you remember what kind of properties? Or you can think of what kind of, you have to think what the properties are of the inner product that you know, the one in RD. Again? Inner product. Inner product. Yeah, so it's symmetric, okay? Order doesn't matter. And again, we can if we let's not do this because we have 15 definitions, so we don't want to go. But we can probably remember like 2 out of 3 of most of this stuff, okay? And then the third one, you just confuse 2 of them typically. So the first thing is the order doesn't matter. The second thing, which is going to be super important, is linearity. This is typically something that makes life easy if you're dealing with something which is linear. And again, this means that if we multiply one thing for the sum of 2, we can split and take the 2 inner products separately, okay? And I'm going to use the word scalar product or inner product interchangeably. It's the same thing. And the other property is that if you multiply one thing for one other thing for a number, so A here and B are just numbers, I can take the number outside of the operation, okay? I can do the multiplication by a number before or after, and it doesn't matter, okay? The linearity. The last property, which is important, is that is the positivity of the inner product, which basically, when I multiply something by itself, I either get a positive number or I get 0. The important bit here is that you get 0 only if you multiply something which is 0 to begin with. There are no two objects in the space that when you multiply, you can produce a 0. One can actually kill the last property and start to get crazy stuff. You see that all this is clearly obviously true for the inner product I showed you in the first slide, the one which is made of the sum of the product of the numbers, okay? But it holds in general. So what do you have to get out of, I mean, this is the first example. What do you have to get out of this, okay? This stuff is on Wikipedia, okay? Why am I showing it to you? Just because when I say inner product, you don't think RD, and you just remember that there might be a situation where it's more general than that. And you see it once, and we're going to do this for an hour, okay? So you're free to leave now if you want. So the important thing about introducing inner product is not only because we see that it's going to bias a bunch of stuff, but is that it allows us to introduce notions like orthogonality. And it turns out that orthogonality is good. It's good especially for computational reasons, for example. We can talk about orthonormal bases. We can talk about orthogonal spaces. We can talk about the null space of this, the range of that. We can do a lot of stuff, okay? The moment you don't have an inner product, you don't have that. So you can imagine how complicated is life. If you want to optimize a function that has an input, a string, good luck. It's complicated, right? Because you're lacking structure. So one of the big things we gain is the notion of orthogonality, which for granted allows us to do what we call an orthogonal decomposition, which means that if we have a big set of a big linear space, we can take a smaller piece, and then everything which is orthogonal to this guy. And this is going to turn out to be sometimes a useful operation to do, because we're going to select what we like and what we don't like, what's useful and what's not. And we know that we can define a split of the space in these two parts. Okay? There is at least one, there are many inequalities, and sometimes you're going to introduce them, sometimes you're going to use them. There is one which you need to know because it's used all the time, and this is Cauchy-Schwarz inequality. Okay? It relates an inner product with a norm. So it's basically saying that if you take an inner product of, and I think probably there is an absolute value missing here, if you take an inner product of two things, V and W, this is upper bounded by inner product of each of the two things you take the inner product, but with the square root. Okay? And the spoiler, this is just the norm of V and this is just the norm of W. Okay? This thing has probably like 15 proofs or more. So if you want to remember, maybe you can pick up one of these proofs and study. They're all 3 lines and algebraic. It turns out that this is one of the things that we use immediately. Okay, you use it all the time. So this is one inequality that you might want to remember. And there's nothing special about it. It's clearly true for vectors that you know. Okay, you're just noticing that this is as long as you have a function of two things with that property, these are just extra property that you get for free. Okay. Clearly, so far so good? Now, as we're saying, not only you don't need, so clearly you don't need coordinates to define an inner product, but before we go on, can you tell me an example of inner product? You know, a linear space with an inner product, which is not this RD, because that one I already told you.
Separability, where the inner product is the complex conjugate of the first times the second.
Right. He basically said our decomplicated version with the complex method of the reals. Fair enough. That's one. And then you have to take care and you have to do the complicated thing that he just said. Any other example? Have you ever heard of signal processing? MIT, say. Take two signals in one dimension, you see them as functions. And what can you do? How do you do a product of two functions? Fancy, but you can just take the product of two functions, right? So you take the f of x, you have f and g, you do f times gx, and then you integrate, okay? All right? How do we call this space of function? L2 is the space of square integrable function. To be able to do this, you will also be able to do a function times itself, which means that the integral of a function times itself must be the integral of the square of a function, so we call them square integrable. Okay, that's the other prototype example. It's kind of the natural infinite dimensional version, prototype of the infinite dimensional version of RD. Okay. Another thing you could do is that I could actually take, instead of RD, put RD with D equal to infinity. That's what we call the small L2. What is small L2? A list of numbers. Each element is a list of numbers, but rather than infinitely many, you have infinitely many. Okay, that's fine. You know, we're just, as long as you have of course, you have to be sure that the series converges, because now you have a sum of infinite stuff. But that's fine. That's another example. Okay, so again, RD, L2 with the big L and L2 with the small l. One is the space of function, one is the space of infinite sequence, are the three examples that you might want to keep in mind of spaces that have linear structure and they have an inner product. Okay, they're the prototype example we will have in mind. If we want to take a step further, we introduce norms. Okay, and it turns out that again, if you have an inner product, you have a norm for free just by this. Take something times itself square root. Okay, we don't need these again to be a sum of numbers. We just learned that, or we just remember that. But remember also that if you have an inner product, we can define a norm. But can we define a norm that is not coming from an inner product? In this case, we have to define. If we don't take this as the definition, we have to define what it is. And there is the similar game. What is a norm? It's something that if you take, is a function that takes one thing and returns a number, which can be either positive. And what you see is that if you take the norm of something, it can be 0 only if I put 0. If now I multiply something by a number, okay, if I check linearity, so to say, I don't quite get linearity. Because if I multiply by a number, and now I try to put it outside of the symbol of norm, I get a positive number. But if I take a negative number and I try to put it outside the symbol of norm, I still get a positive number, okay? You can check this is the obvious thing that happened if you go in the very first slide into the sum of numbers, okay? Because we are taking a square and then a square root, okay? So the square root, they put an absolute value. So this is clearly true in the usual, RD case. If you want a way to remember this is that we are checking linearity of this thing, and we're discovering that it's not linear. It's what is called one homogeneous, if you want to use a fancy term. It just says if you multiply by numbers, you can put them out, but I have to put the absolute value. What about if I want to take this thing of a sum of two things? Does it just split? No, it doesn't, okay? You don't get an equality. If you're checking if this thing is linear, it's not linear, and what you get is that you get this thing here. Just get this, essentially this is a form of the triangle inequality. Okay? The norm of this first guy plus the norm of that is bigger than the norm of the sums. These three properties are what defines what the norm is. Again, what is the intuition about this thing? Well, there is no intuition about this thing. It's just a list of three things. It turns out that everything that you ever call norm in your life turns out to have this. And if you want to invent one, you have to check that this is true, okay? What are examples of norms? Well, you can take any of the example we made of inner product space and just multiply two things by themselves and take the square root. So you can take the norm in RD, you can take the norm in L2, you can take the norm in little L2, okay? The interesting case for this discussion at least is to consider the situation where you can also take a norm which is not coming from an inner product. So let's take RD. What is a norm that is not coming from an inner product? Of what? Yeah, so the so-called L1 norm. What is the L1 norm? Well, you have a list of numbers, and rather than taking the square of each of them and summing them up, you take the absolute value of each of them and you sum them up, okay? This is what you call the L1 norm of in RD. And it's possible to check that this is actually not coming from an inner. It's a perfectly fine function that satisfies all these properties. It's actually easy to check, but it actually does not come from any inner product, okay? And it turns out that it will be useful sometimes to use these kind of norms, and they're going to cost us some sweat because they come from less structure. What about little L2? Can we define a norm in little L2 which is not coming from an inner product? Well, let's do the same thing. If things converge in little L2, we can try to now show them they also converge in when you just take an absolute value rather than the square, and that's fine, okay? That's an okay. What about functions? We had square integrable functions, function for which if you do fx square and integrate is finite. What would be the L1 norm in this case? Instead of the square, take the absolute value, okay? And then we'll call that the big L1, okay? And big L1, you know it because you've seen it before in your life, and it's not coming from an inner product. Now, out of this discussion, you may think that every time you want to get a norm which is not coming from an inner product, you go from a square to something else. It's not like that, okay? For example, if you take a list of numbers, you can actually define a norm by taking the maximum of this list of numbers. This is what you call the sup or the max norm or the uniform norm, okay? This is also a norm which is a legitimate norm, and it does not come from any inner product. And you can play the same game if you have functions. If I give you functions, say on an interval for which the maximum is well defined, in fact, or not, what you can do is that you can just take the maximum of the function value, okay? Among all the value of the function, you take the maximum one. And that's, again, a number you can attach to any continuous function, okay? And that's a legitimate definition of a norm. And of course, I'm just giving you a couple of examples that you probably already know, and you just have to realize that they have this one specific property, that their norm does not come from an inner product. You can invent, there are tons, okay? For example, rather than the absolute value, you can, what we did here, that we take a square and a square root, what we could do is that we could actually try to take something more like a higher order inner product and then take a pth root. Okay? There is a whole set where you try to go in that direction. You define rather than L1 or L2, you define LP norms and so on. We don't want to do it here, and I just mentioned them. It will be useful. We're going to see them and introduce them. Okay? Now you might have got the gist of the game here, and now we're going to do the metric, which is kind of the same. If I give you a norm that might be or not coming from an inner product, I can certainly define a metric. Okay? And so every example, we give example with a RD, big L2, small L2, L1 norm in RD, L1 norm for little L2, L1 functions. For all of these, we can define a distance. But again, you can centrifuge the situation. And the one example I give just as a reminder is strings, for which none of these things seem to make sense. And still we can define a distance. And we have to decide what is a distance. And then we have to introduce a definition, which again is three things that most likely, if I go in the right direction, then most likely you will probably remember. And it's basically the intuitive notion of distance. Okay? One information is if I take distance of things, it doesn't matter the order. If the distance from me and you or you and me is the same, the distance between me and myself better be 0, otherwise we get a complicated space. And then again, we have the Pythagoras rule. We have the fact that the distance between two things, if you add a third point, the distance between these two and the third point is going to be summed up, is going to be bigger than the distance between the two. It's just 3 points of the triangle, and that's all. Triangle inequality.
Vector space. Same.
Typically, you consider, yes, typically you consider linear spaces.
Not a metric.
No, actually, good question. This is not my job, and I don't ask myself this question too much. But all the examples I have in mind are for linear spaces. No, yes, you need it, right? Because even if I don't ask my question, I can still look at the slides, and here there is a plus. And so when I have a linear space, this doesn't make any sense. So this one slide only makes sense if you have linear spaces, right? The plus, it's a sanity check. And also here there is AV. So you see that function takes an input V. So if multiplying by A send me out, I cannot do this. And this is actually a difference between this other line, because if you see for metrics, I don't ever sum or multiply things. So I can define a metric space which is not, it doesn't have a linear structure. And in fact, strings are our favorite example to keep in mind, because that's exactly one case. Okay. All right. Okay, one useful thing that we can do in this space is introduce the notion of basis. Okay. So what is a basis? Well, typically it's something that allows us to decompose one thing as a sum, a linear combination of other things. Okay, so we typically assume linear combination. That what makes our life easy. And one of the main properties of basis is the idea that we can get orthonormal basis. These allow a fast computation of the coefficients. Okay, so if you consider an orthonormal basis, you have then not only you have a decomposition of an element into a weighted sum of some other elements, but also you can compute the coefficients very easily, essentially just by taking inner product. And you see here a first place where the notion of orthogonality starts to pay off, okay, in a good way. And the fact that normalize somewhat allow all the coefficients to be naturally comparable, okay? So this already is a place where you see this be useful. Notice that you probably have met more general cases, but most of the time we think about the basis is typically in this kind of finite dimensional scenario, okay? Where there is no problem in understanding this expression because it's just a sum of finitely many things, okay? So in a slide, I will have to go to the situation where I actually allow my space to be infinite dimensional. And I'm going to keep everything I told you right now, but I will have to worry about the fact that this is going to be an infinite space. And I have to be sure that it always makes sense. Suppose that I want to write exactly what I've done here, but I want to take infinitely many pieces, okay? I have to be sure that I actually get an element in the space, correct? Is it always true? Well, you can invent, and we're going to do it in a minute, example where this might not be true. Okay, you can take spaces and you make holes in this space so that the sum doesn't go anywhere. Okay, the rational number, the real numbers are the example of the positive case. The square root of 2 is the example of a place where I actually picked a guy and took it out. That's the story going on here. Okay, I like stuff that looks like R rather than R minus, the rational numbers. Okay, so that's okay. Hopefully there are not many mathematicians listening to me right now, but that's basically what we want to do. The notion of Hilbert spaces is going to be whatever we just discussed plus something that will allow us to use the notion of basis, meaning that we can make sense of an infinite sum that allows us to decompose things. All right. So as you see in a minute, there is going to be one extra ingredient plus another one. So what is a Hilbert space? As I said, here is basically what I told you. It's going to be a linear space with an inner product, okay? But with something that allows to make sense of this expression, okay? This expression is just one where I already write explicitly the form of the coefficients, okay? But the main point is that you see there is an infinite there, okay? So we have to worry about that and to make this. And these are some of the names that we'll have to discuss. I would say the Cauchy sequence is the main important one, okay? The other two are somewhat coming afterwards. What is the story? I need to be sure that infinite sum converges, and one way I can do it is basically requiring all sequences that are Cauchy. You remember what are Cauchy sequences? Me and not at the slide. You break a bit but it's okay. We'll see in a minute. Wait for a minute until I introduce the notion of separability, and this should answer your question, so that we can share it with somebody else rather than having a private conversation. So what Cauchy means is that, just from what you know, is that if you have a sequence of stuff, say usually for us is numbers, when this sequence, you take a sequence and then you take the same sequence and then you subtract, okay, and then you call it Cauchy if it goes somewhere, basically. Okay, so it's a sequence where whenever two things get close and close, then it goes somewhere. Sorry, not true. So I was confused by this. So we say that a sequence converges if you have this. Already, yes. Let me correct this, otherwise I get confused myself. You say that a sequence converges if it goes somewhere. Okay, you said that a sequence is Cauchy if you take n and m, so two elements, and after a while you see that the distance is arbitrarily small. Okay? You can build crazy situation where you can have this property but not that one. Okay? And again, the reals without the rational number is the irrational number is an example. Okay? Two things get close, but then you're missing wherever they're going. The thing we want to know is that every time you have this property, you have to have that one. So we're going to assume that every time you have sequences that are Cauchy, they should be able to converge. So basically, we're going to assume that the space has no holes. And this is the property that we call completeness. Okay? We're going to call a space complete if every Cauchy sequence converge. Okay? Finite dimensional spaces, we don't have to worry, because again, these spaces are in some sense small. But in infinite dimensional spaces, you have to worry about these infinite sums, and you have to be sure that they always get you somewhere. You first.
Metric as this norm, right? You use norm to define that. Are you going to ever use Cauchy sequences on metric spaces where norms are not defined? Me?
What you can do, of course you can.
So you can.
Yeah, absolutely, yes. So if the question is, can I define whatever I did here without, there's nothing specific. So I use this stuff. So let me give you a spoiler, okay? A Hilbert space is this one line. So it's a linear space with an inner product, which is complete. So it's whatever you knew before, whatever it was the extension of RD that we did 1 second ago, plus this property that every time things can get close, arbitrarily close, they also have to go somewhere. So everything I wrote is having this in mind. Whenever you don't see any particular dependence, there is not. Okay. For example, his question is, can I define this Cauchy sequence for any metric space? Sure. You just replace this norm with a distance, and then it's fine. Okay. I don't do it because I'm going to use it for actually more than just a norm. I'm going to assume an inner product. Okay. So typically what we're going to do most of the time is that we're going to try to work with inner product spaces. And even if we to consider a norm, another norm, which is not the inner product norm, we're going to accumulate on things that are an inner product space. So say I have Rd, I can define the Euclidean norm or the L1 norm. But I already have this big structure to support me in the background. Okay?
There's some holes. Can you just repeat what you said about that? I didn't get that part.
So say, again, there is not the prototype example is the reals and the irrational numbers, okay? So in that case, you can consider a sequence where you have a sequence of things that converge to the square root of 2, say. Yeah. Okay? And at that point, if you remove square root of 2 from your set, you don't converge anywhere, okay? The real line is the prototype of a complete space. Any sequence, it has the property that, it has the property that any sequence with this property is also going to have that property, okay? So in the reals, every sequence with this property also have that property. You agree? Well, you agree, or do you remember because somebody told you before, and maybe just remind you that, okay? The implication from above to below is for free. That's an exercise. You basically put an x in the, if you know that, you just put x in the middle here, you split and it's done, okay? That's not so interesting. But from here to there, you can counterexample. And we're going to say those counterexamples are not part of our world as an assumption, okay? And the fact that these counterexamples are not part of our world is the completeness assumption. That make sense? I'm trying to put layman terms in just basically Wikipedia functionality-like definition, so I'm sloppy by definition. So when I get too sloppy or too annoying, just stop me and I can try to be more precise. Okay, so that's it, okay? So Hilbert spaces is actually a fancy term that you can use at a mathematician cocktail party and be fancy. But in your head, you can basically make it a bit simpler and just say, oh, it's like vector spaces. Okay, I can sum things, I have an inner product. I just have to take care that I want to be able to write orthonormal basis for real. So I have to be sure that the sum converge. And so I remember that this is a story that I have no holes because when I have an infinite sum, it better go somewhere. That's it. Okay, and that word that you want to remember is completeness. And then there's Wikipedia. Kind of. You need one more property, okay, which is basically abstract, and I'm not sure there is any particular, again, these are the prototype example, and frankly, this is this long story. Everything goes back to this. Q is not complete, R is complete, and everything they built out of R is complete. That's long story short. The intuition really is built on there, and then everything else kind of go back to there. Yes? The word boh is very useful. It's an Italian word. It's B-O-H. It means, I don't know. I didn't see it before coming here. Otherwise, I would just delete it. I mean nothing with that. I mean it's a typo. Okay. And again, these are basically the example we already made. Okay. I'm just telling you that they do have this property. Okay. You can check that they have this property. You're basically saying Rn is easy. Everything which is finite dimensional with an inner product, it's fine too. This is the Rn with n going to infinity, okay? And this is the L2 version, the one where rather than a list of numbers, you have a continuous set of values, okay? Keep in mind this guy because it's the prototype example of a Hilbert space. He's the brother, big father or mother of all Hilbert spaces. Basically, all Hilbert spaces that are not crazy can be written this way or equivalent to considering this case. So that's a very important case. That's what we call little L2. Okay, so upfront on technicality, the main part of the story is to remember that we have to add this extra assumption that there are no holes. And the no holes assumption is the completeness assumption, that is every Cauchy sequence converge, okay? Now, let me jump ahead. is this enough? So we are in an infinite dimensional space. Is this enough? What we just assumed so far, the lack of holes, the presence of an inner product, and the Lagrange structure, is it enough to ensure that we can always have orthonormal bases? The answer is no, okay? And basically the next assumption is the separability assumption. The separability assumption is exactly the equivalent to the assumption for us is going to be equivalent to the assumption that we can take orthonormal bases, okay? And I think for our purposes, this is going to be, this is kind of the assumption that you make so often that you typically don't mention it, okay? In most practical papers that use Hilbert spaces, you don't say a separable Hilbert space, because if it's not separable, it's a mess. And you have to build strange counterexamples, okay? So all the Hilbert spaces that you will ever meet in your non-pure mathematician life are going to be separable Hilbert spaces. And so I don't want to spend too much time on this because it's going to be in the background, okay? And it's just going to be the insurance that we can talk about bases. The two slides that I quickly show you are kind of the more precise definition that goes into taking the closure of something and then some countable, then subset, and are going to cause a bunch of questions that frankly don't really matter. So I'm happy to discuss them privately with anybody, okay? But they don't really matter. So we're going to take this first line basically as our definition. Whenever we have a Hilbert space where the probability is to be separable, if we talk about orthonormal bases, period. Okay? Again, it turns out that the example of non-separable Hilbert space are somewhat pathological. Okay, so sometimes it happens that when you go in infinite dimensional spaces, strange stuff happens. Okay, you preserve 90% of what you know, and then some strange stuff happens. The Cauchy sequence was acceptable, right? We kind of convinced ourselves that we need it, that we are be sure to have no holes. This one, I'm not sure I can give you an intuitive explanation why you need it. It's just to fix some of the weird stuff that can happen in infinite dimensions. And so we're just going to take it as something that is always taken for granted. Okay, and so what are examples of again, spaces with orthonormal bases? We're going to take the canonical basis, for example, the usual one. If you consider infinite sequence, we're just going to consider the canonical basis as one example, the prototype example. Is the usual business, as you know, there is not just one. You can rotate and you get another one, and so on and so forth. This is just one example to keep in mind. It's clearly orthonormal. And then we're going to consider probably this as the prototype example of an orthonormal basis in L2. If you take L2 not on the real line, but just on 0, 1, then you can basically use Fourier analysis and introduce sine and cosine and check that these are actually orthogonal in L2. So if you take the inner product just in L2, these are orthogonal and also normalized. Okay. All right, that's it. Okay, that's basically. We're going to use the basis quite a bit, and that's all there is behind this word for us. Okay, the right to talk about a vector of infinite length and also function for what matters, and to discuss not only some things, multiply things, taking in apart other things, but also about orthonormal basis. All right? I'm emphasizing this a bit because typically the effect of this course is, oh, that course is very heavy on functional analysis. We want to use functions, and so we just try to take vectors and abstract those properties that you use all the time so that they hold also for functions. Is this heavy on functional analysis? It's a bit of, you have to just, take a step and change the notation slightly. Hardly ever we're going to really use stuff where you have to worry about the infinite dimensional case. You're going to make assumptions so that even if you're dealing with infinite dimensional objects, you can deal with them as if they were vectors. Okay, that's kind of how the whole course is designed. We're going to do functional analysis so that if you forget dealing with infinite dimension, it's just linear algebra. Okay. All right, now we want to go and talk about maps between spaces. Okay, and the first map we can do is from the space, which is a linear space, into numbers. That's what you call a functional. Okay, a functional is simply a map that goes your space, and typically the symbol you use for Hilbert spaces is surprise is H. Okay, and then a function is what goes into number, and an operator is something that sends a space into itself or into another Hilbert space, maybe not itself. Okay. The prototype example is, what is an example of a Hilbert space? A simple one is RD. What is another example of another space which is not RD? RP, okay, with P smaller or higher, okay? What is an example of an operator? A matrix, square, rectangular, okay? What is an example of space which is not finite dimensional? L2, okay, big L2. And let's say an operator goes from L2 and L2, you actually mentioned 3 minutes ago, convolution. If I take two functions and I use one, but rather than just make it the product, I take this function and the other one I move slightly time, and I take the product of the function and the moved version of the other. That's what you call a convolution, as that's an operator. It takes a function and returns a function, okay? Is it a matrix? Well, until you discretize something, no, okay? But yet, most of you have probably already met him. So here we're just giving it a name, and we're just gonna call operator whenever it's not just numbers. Then, of course, we can enter in discussions like, okay, but in the end, to implement things, we want to, we don't want to enter in that discussion. You know, the fact that working in continuous limits is useful in a bunch of situations is debatable and yet been quite successful over the years. All right, so one basic result that we're gonna introduce, we're gonna use tomorrow, actually, is a very deep result, by no means something that I ever understood to the level of be able to give you an intuitive explanation, and it's basically the fact that if a functional is linear means the usual thing, I can multiply by numbers, then it means that I can always write it down as an inner product. This is a very deep fact, okay? It's by no means an obvious thing. Whenever you have something that given a function returns a number with the extra property that it's linear, okay? And continuous, okay? With continuity is defined the obvious way. We're gonna see this tomorrow. Actually the one incomprehensible result, and we're going to use it tomorrow again. So I'm just going to repeat it again slowly. The point is that if you have a function which is linear and continuous, then you can always write it in the inner product. That's a very nice thing. You basically said that there is a family of functional that has a special structure. It can be linearized. And one thing you might want to remember, linear is good. We like vectors because they're linear. Okay? And we like linear functions because they're simple. We can use a lot of structure. Whenever you're dealing with no linear stuff, it gets complicated. Okay? Neural networks are complicated because they take any pieces of linearity you have and they kill it. No linear dynamical systems are complicated because they are non linear. And whenever you see non linear, it's a mess. And how do we study it? We sweat like hell to try to bring back the linearity hidden somewhere. So that's why we always, whenever you see something linear, we are happy. And this is one case. These functional that are continuous, boom, they're linear. Okay, so that's good. Same thing for the operator. We are not going to even bother discussing nonlinear operator. We are always going to discuss linear operator. So matrices. Okay. The bottom line of the story is that you know, if you have a function, so the convolution operator, unless you discretize, is not written as a matrix in any sense. Once you put coordinates or you choose a then you can write everything down as a list of numbers, and operators also become list of numbers. Okay? So the difference between a matrix and an operator is typically the choice of a basis or a set of coordinates, if you want. There is one notation that I sometimes use, and I certainly use in the notes. It is the notion of the transpose or the adjoint. Okay? These are the same thing. One is the name used for matrices, the other one is basically the name used for operators. We typically, you know, if this is a matrix, if it's rectangular, when you write it the other way, that's what you call a transpose. There is actually a one line that describes this operation, which is basically when you take the inner product of something else where you when you apply the matrix. Okay? And you say that the matrix is the transpose if you can basically move this one from here to here. So in this notation, the way you define a transpose is the one matrix for which you can go from this line to this line. What's written in the middle is just the version that you might be more used to if you write things in terms of the transpose notation with the T on top. Okay? You have this, and then you can write this. Okay? You take the transpose, you have to put it here and switch the order. I personally find, after a while that you look at this, typically you find it easier. Okay? But the time you see it, if you're used to this, you have to remember it. So this is one line that you might want to write a couple of times on a piece of paper, just to remember. Okay? That's it. So the transpose, this is the definition of transpose, and this is just the usual notation, and this is the notation with the bracket for the inner product. And of course, something is symmetric if it's equal to its transpose. Okay? If I look at it this way or this way, and it's the same. If you're dealing with matrices, a notion that we're going to use all the time is the notion of eigenvectors and eigenvalue. And I'm assuming I don't have to repeat what these are. A couple of things that we might want to remember is that if a matrix is symmetric, it means that if when you look at the eigenvalue, they're all real. Okay? And another thing that we use oftentimes is that, well, let's see, where is it? Okay. We often use the eigendecomposition. The eigendecomposition of a matrix is something which is really nice because, okay, you've seen it, this is what it is. It basically says I can always write the action of a matrix as using some basis and then multiply by numbers. I'm not sure if this is the way you thought about it, but this thing is beautiful because it means that any linear operation I can just think of multiplication by numbers after a change of coordinates. So that's nice. Okay? It's again a form of extreme linearization because it goes from high dimensional to essentially one-dimensional operations on some diagonal matrix. So that's nice. We're going to use this a lot. It's going to be very useful for us. I'm not sure we're going to use it a lot, but we're going to use it a bunch. The singular value decomposition, and again, is something I'm assuming you have seen one way or another in your life, is just basically going to be an extension of this in the case where rather than symmetric square matrices, you actually are dealing with a rectangular matrix, and I give you a similar decomposition. Okay? We don't want to deal in the details of this too much. One thing that you might want, again, to write on a piece of paper, this is one way I like to write the SVD. This is probably the way you're mostly used to, and this is another way. It's very easy to convince yourself that this is completely equivalent. These two things are completely equivalent, okay? And then a legitimate question is, if I have one line to write one thing, why do you want to use 4 lines, for equality? Because this is kind of nicely operational. This is basically saying, oh, look, I can build this square matrix or this one. They have the same eigenvalues, but different eigenvectors. But if you give me this eigenvector, I can go back to this one by performing this operation, applying the transpose. Okay? Same. If you give me the eigenvectors of this matrix, I can go to the other one by performing this other operation. It's going to be useful for us. Sometimes it's going to be useful because we're going to have the data space or the feature space. We want to go back from one to the other, want to do some operations. And this is actually of course, there's no, they contain the exact same mathematical content, okay? They're completely equivalent. I'm just saying that this, from a semantic point of view, bring in some form of more operational comprehension of what is the SVD doing. It's providing set of bases and then a way to transform one set of the bases into the other one. So again, not much going on here, but you might want to write this down briefly somewhere. When talking about norms, sometimes you're going to talk about norms of matrices. Okay, what are norms of matrices? Well, so matrices turns out to be an example of a linear space that we haven't mentioned yet, but they are. I can sum up two matrices or multiply by numbers, and then I can keep on going and define norms in their product and whatnot. The most, I guess, the most natural example from if you come from vector is the so-called Frobenius norm. Okay, this is basically the trace of something transpose itself, and you can write it this way, and you can write it in many ways. It's equivalent to the usual Euclidean norm for matrices, and it comes from an inner product. It's called Frobenius norm or Hilbert-Schmidt norm sometimes. The one that is actually often used is the spectral norm, okay, or this is basically the uniform norm. In this one, what you do is that you actually have to take the maximum singular value, eigenvalue of the matrix. And you can keep on going. Again, also in this case, you can define some kind of L1 version, an LP version, and so on and so forth. And when it will be useful, we're going to talk about this. At this point, you just want to remember that matrices are actually an example of a linear space with all the properties that we've been discussing so far. So here you see, what's happening there? So let's say, if you can just look at the first one, this is just a singular value, okay? Otherwise, when you do this, this is basically lambda max is going to actually be the A transpose is lattice slope, is like the square root of the absolute value of that number, okay? In general, that's how you define it. Most of the matrices we're going to deal with are going to be nice matrices, and this is not going to be a problem. One other property we're going to use all the time is the property in positive definite, okay? And this property can be written in two ways. One is that the easy one is that you diagonalize this thing and you check that the eigenvalues are either all positive or at most zero. In one case, you call it positive, because it is positive semi-definite. Positive definite, in other case, positive semi-definite. You can also rewrite this property as a quadratic form. You take something, apply the matrix, and then take the transpose. That should be a capital transpose according to the previous notation. There are two ways to say the same thing. Again, here I'm emphasizing the fact that these things are defined in the finite dimensional case just by using the vector notation. But basically what is going to happen now is that I'm going to rewrite the same thing with just slight adjustment in the notation, okay? Let's skip this because I don't care. This is the notation where you're dealing with operators. So it's the same one I emphasized before. The star over there is the notation that is typically used in place of the T, okay? It's basically something that is useful when you're also dealing with complex number and real numbers. So that's the main reason. But for us, we're always dealing with real number, so they're going to be more or less synonyms. The word that you use when you talk about operator is not symmetric, but sometimes you actually use the word self-adjoint. Okay, so sorry. Operator is the transpose is called the adjoint. Okay, and the symmetry properties is referred to as the property of being self-adjoint. Okay, so again, these are a couple of names. So if I use this word, just go back to it: adjoint, transpose, self-adjoint, symmetry. Dictionary of terms from the finite to the infinite dimensional case. Now, this last line is actually, you can appreciate how incomprehensible it is. But these guys are going to be important, and we're going to basically deal only with operators, okay? What's the story here? You remember convolution operator? How do you study a convolution operator? The easy way is that you do a Fourier transform, right? And then it just becomes some kind of multiplication. Well, the convolution theorem is that. Do people remember this result or remember that somebody told them this? It's nice because you linearize something and it just becomes a multiplication. It's not nice because you have no sums. You have to keep on worrying and doing integrals. And we actually like vector and matrices. So we do like the situation where you can actually write things down as matrices, okay? What you need to do to be able to write things as matrices, you have to be able to do the same thing with convolution, but get some kind of sums. Okay, you want to linearize and get sums. That's basically what compact operators are doing. In general, so the convolutional operator has eigenvalues and eigenfunctions, but they're not discrete. That you have infinitely many. That's exactly the Fourier transform. The Fourier transform is diagonalizing the convolution operators, but you have a continuous of eigenvalues and eigenfunctions. Okay. I'm just going to repeat it to sink in. When you do the convolution operator in general, you're diagonalizing it by taking the Fourier transform, but the Fourier transform gives you an infinite list of eigenvalues and eigenvectors, so to say. The compact operator are those that don't have that property, but are the ones that are similar to matrices, where you have an infinite list, but discrete, countably many. Okay, so you just get back to countably many possibilities. So you have a list of numbers. It's a list. It's not a continuous of numbers. It's a list of a countable list of numbers. Okay. So what are this is the insane metric definition of compact operators. But what we're going to use is that compact operators have the properties that when you diagonalize them, they have countably many eigenvalues and corresponding eigenfunctions. Okay. And so you can, for us, we're going to always consider the case where these eigenvalues are real numbers. So we're typically going to consider operators as symmetric, positive definite, and compact. This means that they look like matrices for which when you diagonalize them, you get just a basis that look like a basis. And the eigenvalues are going to be positive number that at most can be zero. And in fact, zero is where you have a bunch of stuff accumulating. Okay? If you have infinitely many eigenvalues, zero is the only place where they can accumulate. That's what's going on here. So long story short, they have in principle a nasty definition, but these are going to be the operators that we can look and we can think of them as matrices, big matrices, infinitely large matrices. So again, we can of course discuss and give you much more detail of this, but that's not the point of this. So I'm just giving you the high level definition. Sometimes we also want to, this definition is the definition that basically says that if you take a ball here, it's going to be squeezed into an egg into the other space. That's the other way we want to think about when you think about compact operators. If you take a map from RD to RD, and you take a ball in the input space, so you apply this to any vector in a ball, we're going to squeeze them somehow, okay? We're going to squeeze them in some direction. And the direction are going to be exactly the eigenvalues, and the length of the squeezing is going to be, the eigenvectors, and the length of the squeezing is going to be the eigenvalues. That's going to be what's going on here. So again, compact operators are actually very friendly objects because we can look at them as matrices, okay? And matrices that takes something and squeeze it in some directions, okay? Again, I'm really abusing things a lot here, but that's basically trying to convey what are the main ideas, and the rest is really not much more than digesting Wikipedia stuff. Again, the nice thing about compact operators, you can write, remember this. This is nice, right? Try to write this down for the convolution operator. You cannot, because there is no such thing. But for compact operator, we will be able to do it, okay? So the spectral theorem holds the same way for compact operators. It's more complicated for non-compact operators because you have to write integrals in scalar. But if you're dealing with compact operators, it just looks the same. Again, this is exactly the same notation as before. I only replaced the transpose notation for inner product with this notation. I take any element of the Hilbert space, I take the inner product, I get a number, I assign it to this function, and then I have to multiply by a number. Explain the action of a complicated object just by the same way you would do by diagonalizing a matrix. So this is going to be useful, and we're going to use it. All right, we're almost at the end. Let me just recap a bit because this is already pretty painful. Again, we're going to deal with infinite dimensional objects, and we basically just want to emphasize how and how much we have to learn anew, okay? And of course, there are tons of details, and if you want to work in this kind of stuff, you have to gain some knowledge of functional analysis, but you can go a long way without, okay? Just by remembering whenever you have to be careful applying your vector reasoning to infinite dimensional object. And most of the time, an assumption is going to be enough, okay? So the basic idea is just remember there are sets with different structures. The most basic one is having an inner structure. It can be, there might be examples where you don't even have that. Strings is the main one. And then these different notions, metric, norms, inner product, which go from a weak assumption to a strong assumption, because once you have an inner product, you can go back, okay? But these things leave, oftentimes we think as the whole story, but actually these objects live an independent life, and they can meet or not, okay? RD, L2, L1, big L2, big L1 are the example you want to keep in mind. The space of continuous functions, perhaps, are the main example you want to keep in mind. These little changes, the bracket-like, the transpose-like. Then we move on and discuss maps from the Hilbert space or vector space to something else. Right, sorry. So Hilbert spaces are this guy, infinite dimensional, where the big role is played by this notion of completeness plus a technical assumption, separability. Okay? And completeness is the fact that since we want to do orthonormal basis, we have to be sure that we can talk about convergence of infinite sequence without having to worry about the fact that there might be some pathology. Okay? Of course, we have to worry that series converges, but we don't have to worry that even if in some sense morally they should converge, they don't, because I actually deleted the one point where they should go. It doesn't happen. Okay? That's basically what Hilbert spaces are going to be about for us. Then we talk about maps between spaces, functionals. Functions are going to appear all the time for us because we want to minimize errors over functions, but we're always going to try to massage them to become something similar to function over vectors. Okay, and it turns out that if you remember what the directional derivative is from the multivariate calculus, basically the same definition holds if you're dealing with Hilbert spaces, okay? And the same kind of theorem holds. So up to a little abstraction, you're going to be able to use roughly the same thing. Of course, digesting stuff takes time, but 90% you already know what I'm trying to emphasize here. Then the matrix operator business. It's just a name matching business largely, okay? We only think of matrices as a list of numbers. Now we have to also think of them more as a convolution operator, more as a more complicated operation. They're going to try to work hard to make to make it look like a matrix. We're going to talk about eigenvalues, eigendecomposition, singular value, symmetric, positive, and so on and so forth. These names change slightly when you go to operator. Symmetric become self-adjoint, transpose become adjoint, and this notion of compactness turns out to be useful because one case where we can find a countable sequence of eigenvalues and eigenvectors, which allows us to write things as if they were big matrices. Okay, operators become big matrices, and again, the convolution operator that somebody recalled is kind of the one example that you might want to just work out as an example of this story. That's basically it. Just really 4 slides about, first of all, do you have any questions or doubts or something? Again, this is intentionally sloppy, and the intention of this is just to show you how things that you know in RD can be largely extend. We're going to work in a setup so that you can think about infinite dimensional objects basically in the same way, so that function analysis become linear algebra. You can work with non-parametrics as if you were doing parametrics. This is the game we play, okay? Because whenever somebody says, oh, that course is so heavy on function analysis, kind of. You have to remember 10 words and just map them with linear algebra. This course is heavy on linear algebra especially. All right. Probability spaces. This is really 3 lines of Wikipedia-like stuff. Random variable, the fancy version. You have a set where you have a notion of measurable spaces. These are sets with some properties. They're kind of are the sets where you want to define probability. So you need the whole thing, you need nothing, and you'd be able to say what it means to sum up things. Okay. So the basic property is that if you take a sequence of disjoint, an infinite sequence of disjoint set, doesn't have to be disjoint, the union of the set, even if an infinite belongs to the space, is a technical, is the basic technical condition. It's related to the fact that we'll want to, the way to remember this is that to remember in probability, you want to map probability. That's basically the one property that allows to be sure that you can talk about summability of probabilities. And if you want, when you introduce probability, it parallels this. Is a function that to every, say, the real line is the prototype example, okay? Probability space, say the real line, then you have to define this notion of sigma algebra, is this family of sets. What is it? Open sets, the so-called Borel sigma algebra, the prototype example. Then we want to measure the size of these sets in such a way that it sums up to 1. Okay, that's the basic story, and that's what we call a probability distribution. A probability measure takes any set, say open set in the line as an example, and say how big it is with a few rules. If you take nothing, it should be long 0, it should weight 0. If you take the whole thing, it should not be infinite, it should be 1. That's actually a pretty important typo. And then it has to have the sigma additivity, the story that probability should sum up. And basically, if you take the probability of a union of things that don't overlap, this is just the sum of the probabilities, okay? And you want to be able to put infinity here. And that's why you allow yourself to be sure that whenever you take infinity, it's still in the space. Otherwise, you will violate the fact that you have to apply this function on these sets, okay? To remember this, which is kind of the exotic, is the one exotic story in all the slides, is to remember that you want to do this, that you probably will remember. Okay, so this is the basic definition of a probability space. Random variables, the two things sometimes get blurred after a while you use them, but a random variable is actually a function on a probability space. It takes a probability space, which is this abstract stuff. It doesn't have to be real, it doesn't have to be crazy stuff. Again, for example, for us, the input space is going to be the input space. Okay, it's going to be a probability space. And again, it can be the space of graphs, it can be the space of strings, pretty crazy stuff. Okay. All the structure you need is that. You need to be able that there is some minimal structure that allows to define the probability distribution. And these are mostly going to be technical requirements. But again, this is just to say, when we talk about probability space or input space, these are not just RD, it can be general stuff. And we want to be sometimes general to account for exotic example of structured data sets. what is a random variable is actually a function from a probability space to some place where you can define a probability distribution, where there is a sigma algebra. And I think for 90% of the course, we're just going to talk about real valued random variables. So you take a probability space and you send it into the reals. Okay. So now you, in some sense, you want to transport, not in any technical term, you want to put the distribution that you had into this new space. Okay. So the way you do this is by defining a distribution on the output space of that function, and this is called the law of the random variable. The notation is interestingly complicated, but it actually says the obvious thing. It says if you have a domain here where you know how to measure how big are things, and you want to learn how to measure things in another domain, well, take the function that gets you from here to here. Take any set that you want to measure here, pull it back, and then measure it, because you can do it. That's what's written here. Again, I don't have a drawing, and I'm using my hands, but you see it enough. So you basically say the interval is in the real line. I have a function that goes from my probability space to the real line. Let me take this interval and plug it back. Okay? And then let's check how big it is. That's the size of the interval. And that's the definition. That's what you call the law of the random variable. And that's how you pass the distribution over omega, from omega to R. Again, these are a simple situation, and in typical cases, what you have is that you can actually give a nicer expression to that function that goes from sets, and you can just write it not as a function over sets, but as a function over real numbers. And that's the notion of density. If you write things in this notation, it basically says, if you want to give me the full measure of this set, I have to integrate with respect to this measure. If you have a density, it means that you can actually write this down as some real valued function that is somewhat a point-wise measure how much this distribution changes with respect to some other distribution. Now, I don't want to spend too many words on this for a couple of reasons. This is an object that is probably familiar to everybody, and you give it for granted. It's actually an object that to define precisely requires some sweat and define some thinking about something that you typically don't think of, which is how much that this varies with respect to an underlying measure, which is usually the Lebesgue measure. And this is the so-called Radon-Nikodym theorem, okay? And we don't want to think about that too much. It doesn't really play a role. I'm happy to discuss this with anybody. It doesn't really play a role. You just want to remember what I told you yesterday, which is that we're often going to use this notation just because this requires some effort in the situation where the domain is not the real line, but is something more complicated, like a manifold or a subset or a complicated stuff. And somewhat we want to be somewhat oblivious to what is the underlying set. Okay? And so sometimes we typically prefer this notation, mostly as a reminder that there might be some issue in defining this exactly. Okay? Not more than that at the level of discussion we want to keep. All right, so I'm assuming that this stuff is more or less familiar to everybody, and I'm just going through it. One thing that we're going to discuss every once in a while, and it's good to have there in the background somewhere, is the notion of convergence in probability. And this is basically the idea that if you have a function, okay, which is not just any function, it's defined on a random, on a probability space, you have to worry what does it mean that it converges, okay? So you have a sequence of numbers, which is stochastic. What does it mean that it converges? Does it converge? Is it a specific, when I have a sequence of random numbers, I take a sample, and then I want to know if is this sample that converges? Is any sample that converges? Is the sample that converges on average? For most samples it converges? What does it mean? Okay? And so this is why you talk about convergence probability. You need to make sense of what does it mean for a sequence, possibly infinite, of random numbers to go somewhere. And there are typically two ways of doing it. One is the most, somewhat less ambitious one that says, the probability of keeping a sequence that is far away from something is small, okay? It becomes very small. You basically this measure the amount of bad situation goes away. The other one, which is a bit strong, is the one that basically says that the bad situation don't happen, okay? It says that the fact that this goes there is certain. This is the probability becomes smaller and smaller and disappears. This one says strong, okay? This is what is called the convergence in probability of weak convergence, and this is what is called the strong convergence or almost sure convergence. Okay, there's something similar to weak convergence of function or sequences of pointwise convergence. Okay, or almost sure convergence. us, we're going to use this mostly to do stuff like this. There's a general idea that if you have random events, you can use them to learn something about some underlying phenomenon. It's, of course, everywhere in machine learning. And the typical idea is that if you take an empirical average of a sequence of identical and independent random variable, if you actually allow this sequence to infinity, you take the mean over more and more things, it's going to go somewhere. Okay? And if you apply the law of large number, the definition of convergence probability to this specific random variable, which is the sum of n random variables, then this is what you call the weak law of a large number. And you do the same thing, but you apply the almost sure convergence to the sum of values. This is what you call the strong law of large numbers.
Like, why do you?
You have a situation where this is true and this is not. I mean, this implies this and not the other way around. Okay? Yeah, it's not. It's about. So these are just definition, right? I'm not telling you. So that's definitely not enough to ensure this.
Okay.
So this is not a theorem that says if you take those, then you have this. It says for those you can define. Now you're asking a different question, which is under which assumption on those you have this, and typically you need some kind of regularity. Okay, and the next slide provides some basic, some basic condition that that ensure that this is true. For example, if you have the simplest one is something that does a bit more than just providing a limit, but actually find an actual upper bound to the probability of the bad stuff. So we're talking about now the weak convergence in probability, not one, okay, which is mostly what we care about here. And it's basically this is saying if you have a sequence of random variables that are identical and they have a finite expectation, so very reasonable, you can already bound that, okay, and you just have this very weak dependence on this pretty bad dependence on epsilon. You can, if you, sorry, this is wrong actually. You have to correct. You should not have that sum there, okay? This is, I'm mixing up the two slides before. Instead of the sum here, just consider the case where you have a random variable and its mean, okay? A random variable and its expectation. Maybe I should just not show you this and show you tomorrow. So this is a random variable, and this is its expectation, okay? And it's able to bound this quantity. Chris, can I switch to the board? Because that's too bad of a... So let's first do it for one single random variable, okay? I would like to show stuff like this. Like to control this, okay? I want to show that, sorry. We're going to infinity that this goes to 0, okay? The limit for I goes to infinity of the probability of xi minus ex bigger than epsilon goes to 0, where all these xi are all identical and they have the same expectation, okay? How do you... This is the definition of a sequence of random variables that converge weakly. How do you prove something like this? You have to make some assumption, okay? And concentration inequalities are one way to do this. You basically find a way that under some assumption to give it, not only to show this goes to 0, but to actually provide a specific bound, okay? Sorry, specific bound, not 0, okay? The first one is Markov inequality. This is an exercise to prove. Okay, just this is like a one-line proof. And then you can make this fancier. Okay, you can try to get sharper inequality. For example, you can try to, if you have more assumption, for example, you say not only know that they have the first moment, but I also know that I can go on and have higher order moments. You can consider, for example, the variance, in which case you can put epsilon square here. Okay, so the basic idea, and it goes back to his comment, you can actually get the stronger assumption you make, the stronger result you can take. Okay, you can derive. And then you can keep on going. I can give even a stronger assumption here, and the one I put there. If you know that the random variable are bounded by a constant c, you can get something like this, an exponential concentration. This is actually much nicer than this. Why? Well, just check and try to answer questions like, what is the probability of a random variable be 3 times the variance away from the mean? Okay, the 3 sigma question about the Gaussian. We know that if it's a Gaussian, there are tables when you go to derive it, it's like 90, 99, 97, I don't remember. Okay. That's because you know exactly that it's Gaussian. Here I'm just telling you, I don't know if it's Gaussian, but I tell you what the variance is. Then you can go in and plug in a number and see what is the number you get. And here you get a pretty bad confidence. The probability of being 3 sigma away is going to be very low. Okay? It means that you don't know that everything is very close to the mean. You actually can make much weaker statement. If you can get something like this, you can get close to this. So what I'm trying to tell you here is that for us, asymptotic statements are going to be interesting, are going to be sanity check. These kind of results are going to give not only asymptotic statements, but also things about how quickly things get become 0 or get close to their mean. And typically this will translate into a statement about how many samples I need to achieve a certain accuracy. Okay? And we'll see that it's kind of a better stress test for our algorithm. It will reveal more about their theoretical properties. But this course is largely not on this kind of properties. So I think this is basically it. Sorry for the last typo, I'm going to fix it. I think this is basically it. I will let you go. If you have any question, I'm going to take them offline.